Hello, welcome to the latest edition of SYCL Sessions. My name is Rod Burns. I work at CodePlay Software, where I'm a strong advocate for open standards, including SYCL, and I work on helping to educate and support developers. I'm joined as ever by Dr. Tom Deakin from the University of Bristol. Hello, Tom.
Hi, how you doing?
Yeah, good. It's been a while since we last did one of these, so there's probably plenty to talk about. This time we're joined by Andrey Alekseenko from KTH Royal Institute of Technology in Sweden. He works on the GROMACS project, which he'll tell you more about during his talk. So thank you so much for joining us, Andrey. We're looking forward to hearing more about your work with SYCL. So Tom, it's been a while since the last edition, and so long, in fact, that we've seen iWACL and SYCLcon come and go. So perhaps we could spend a bit of time talking about that. I guess you were quite involved in iWACL and SYCLcon again this year.
Yeah, I was on the program committee, so reviewing some of the technical papers, and I also chaired the panel session, which is always a really nice part of iWACL and SYCLcon.
Yeah. So the panel session you were on, that was interesting. I had some different conversations on that about like different targets like FPGAs. I heard some discussions about new features and even C++ like ISO features, I guess, like MD-span. And there were also some conversations, I think, on, I guess, how to bring in new experimental features to SYCL through like extensions, which I suppose is something that's quite crucial about SYCL, is the ability to add new functionality to, I suppose, test it and prove that it works through extensions, which I think is an interesting feature there. I guess, what did you think were some of the key discussions that happened on the panel this year?
Yeah, I thought it was a really good panel. So for those that missed it, you can now catch that on the website, on the iWACL website, so you can go back and catch it all. But yeah, as well as talking about new features and extensions and how we might be incorporating those extensions into the SYCL standard. There was some nice discussion about safety critical, why a safety critical version of SYCL is interesting and useful and needed in things like automotive industries, things like that. So that was really interesting. I would catch that. There were some other talks about that during the week as well. So lots of content there. I think some of the other stuff I really liked about the panel was some of the more sort of high level discussions. I used my prerogative as chair to ask some difficult questions, and the question I asked was about what SYCL has brought to heterogeneous compute, and it was nice to see the panelists attempt to answer that, and I think they had some really interesting answers. I think the other thing we talked about was where SYCL's going, what the future might be, and what the relationship of SYCL is to standard C++, and the whole kind of how C++ is moving forward. We're recording this in 2022 in the summer, and C++ 23 is very much being formed, and we expect that to be released soon. But SYCL 2020 was based on C++ 17, so all these things are moving forward and making great progress. And yeah, there were some really nice discussions about what the future holds for SYCL and what the future holds for C++, and how those two paths are going to intertwine and things like that. So yeah, it's lots of interesting things in that session.
Yeah, excellent. Yeah, I guess, and we'll also include some links and things like that, so you can find those easily. So one of the things I was thinking about is you have I suppose, a bit of a special role within Khronos in terms of being a bit of a conduit between developers and, I suppose, the working group and other parts of Khronos. So I guess what's important for you from the iWACL SYCLcon conference and facilitating that, do you think?
Yeah, so for those that don't know, I'm the outreach officer for SYCL within Kronos, and my job really is, as you say, this conduit between the working group and the users, but also some of the official roles within Kronos, things like the marketing team and things like that. And marketing sounds a grand word, but really it's how SYCL is presenting itself to users, right? That's the focus. So a big part of this is understanding the sort of feedback that we get. So things that work, things that don't work, what features are important to different areas of users. And yeah, the conference and the discussions that we were having all around iWOCL do help sort of allow us to collect that information and bring that back to Kronos, to the working group, and help, direct where the standard's going and resolve some of those pain points. It's also useful as well, as we know a lot of the implementers take part in those conversations too. So some of the feedback on implementation issues gets passed straight back to the implementers as well. So yeah, it's really important that we can have these conversations, and doing it at a conference, even though it's a virtual one, is a nice way to do that.
Yeah, that's good. Excellent. I think one of the main sort of news points, if you call it that, was around iWOCL, was this open sourcing of the so-called SYCLmatic, I guess I got that right, project, which is the open source version of the DPCT converter, which is a tool which you can give it CUDA code and it converts it into SYCL. I know that at least one of my colleagues has used that to convert some code from CUDA to SYCL, and find it like a very useful aid in that porting migration process. And I feel like open sourcing that can only be a good thing from the point of view of it means that people can kind of see how it works and even modify it or even suggest improvements as to where things don't quite work, because it's quite a difficult thing to do, to convert from one programming and model or environment to another. So I think that's a good step in the right direction. I don't know if you've had any experiences with that tool or what you feel about the open sourcing of that.
Yeah, I think open sourcing that is great. I think it's a great idea for a tool to help move away from a proprietary model, and whatever that happens to be, into something that's more open, that enables you to run both on the hardware that you came from and others. I think, as with all tools, it's a useful first step, and I expect there'll be lots of tidying up to do. I saw lots of presentations on this at the ISC conference that happened in June as well, or end of May maybe. And yeah, I think people were saying that as a tool, it's quite good. It gets you nearly all the way there to a functional port. There's some tidying up to do, and then you can think about maybe some performance optimizations. But anything that's sort of building on and building out the ecosystem for SYCL is a great addition. So yeah, it's good to hear.
Yeah, definitely. I think it certainly also makes it a very quick way to kind of experiment with some SYCL code compared to CUDA as well. And as you say, whilst it may not give you a perfect output, it certainly goes a long way to helping you to get towards that. So that's good. I think the last thing I was going to talk about was the keynote from Axel Alpe, who Andrey mentioned as well. He was talking a bit more about how SYCL has been developed to target lots of different hardware. I guess if you don't know, SYCL is one of the SYCL implementations. It's open source. It's developed by an academic group at the University of Heidelberg. I suppose one of the things that Axel said I found interesting was he said it's a myth that SYCL support from hardware vendors is needed for stability and performance. So I suppose the crucial thing here is that, and what Axel's group has proven, and others as well, is that you don't necessarily need the hardware vendor to implement SYCL support, and that SYCL has that flexibility that you can plug it into the native like instructions or tool set for a particular target and run it using the same path and the same set of instructions and get comparatively good performance with the native version as well from a vendor. I thought that was quite an interesting insight from things.
Yeah, that was interesting to hear. His keynote's great. So if you haven't seen that, I would try and catch that too.
Yeah. I think one of the other things he talked about, which I know my colleagues have talked about before, is this idea of kind of incremental porting. So if you're moving from something like CUDA to SYCL, then the interoperability that allows you to convert a bit of your CUDA code and still run them kind of at the same time, so that you aren't in this situation where you have to try and port all of your code at once, test everything, make sure that it works and everything else. You can kind of do a bit at a time and validate that and kind of move on. So I think interoperability is another crucial part for SYCL too.
Yeah, and there was a nice talk as well that talked about interoperability. There's a few different authors on that, but they talk about the different modes and some common and some more uncommon use cases for that interoperability layer. So that's quite a fun talk.
Yeah, no, good. Were there any particular talks that you would draw people's attention to?
I mean, all the program was great again for iWOCL and SYCLcon. So it's a little bit like, a kid in the sweet shop. You can take your pick and you'll get on okay. But I really liked the talk from Philip Saltzman from the University of Innsbruck, talking about their Celerity project, and it was kind of a high level talk talking about how SYCL could be extended to consider a distributed system. So not just a single heterogeneous node, how the programming model can be extended for multi-node. There's a great talk from some people at Intel, headed up by Mike Kinsner. And it was really interesting looking at how, say, a SIMD style parallelism is exposed within SYCL and the challenges an implementer has on mapping that to different types of hardware that are being targeted. So how might SIMD look on a GPU and how might it look on a CPU, and how is it exposed in the model? So that was kind of fun. And yeah, we'll hear from Andrey a bit in a moment about their work with GROMACS, and there were lots of talks from other science groups at iWOCL and SYCLcon as well. There were some people from NAMD, and people doing some drug discovery and some linear solver stuff. So lots of different scientific domains are kind of trying out SYCL, and it's nice to sort of see how they're getting on and some of the progress they're making in those domains. So yeah, I think there's lots for everybody.
Yeah, no, I found the NAMD presentation was interesting from the perspective of understanding a bit more about the science behind things, as well as the experiences that they've had in kind of going down the route of using SYCL for different targets. So yeah, I definitely second that. Okay, so you can find all the presentations on the iWOCL SYCLcon YouTube channel. Probably the best place to start is to just go to iwocl.org, and that'll point you in the right direction, but we will include the links in the video too. So I suppose let's move on to the main event and move on to our speaker, Andrey. Thanks so much for joining us, and we look forward to talking more about your presentation afterwards.
So today I'll talk about our group's experience in using SYCL in GROMACS for performance and portability. I'm Andrey Alekseenko from KTH in Stockholm, and this talk was done in collaboration with my colleague Szilard Pál, and of course with great help from the rest of the development team. So what is GROMACS? It's a high-performance application, a molecular dynamics engine, which is quite popular. There are a number of metrics to check to show it, but yeah, I looked at Google Scholar today, and there are more than 3,000 papers mentioning GROMACS and the COVID research. So yeah, of course, not every single paper uses GROMACS, but I would say it shows that it is indeed pretty popular and widely used in the research circles. And it's also one of the most used high-performance codes worldwide in general, according to a research from a few years ago. GROMACS accounted for around 5% of supercomputer usage worldwide, and together with other MD engines, it was around 15%, at least, of the supercomputers that are more or less publicly available. So yeah, it's a pretty big application that runs on pretty big machines, but we don't limit ourselves to that. We also want to run on laptops as part of the Folding Home project, the grid computing initiatives for protein folding that's run by volunteers all over the world. And we want to run on multiple systems, of course, the typical x86 CPUs, but also ARM, Power, Spark architectures, and like many other MD codes, we also extensively use GPUs. We are actively targeting NVIDIA AMD and support Intel GPUs that currently are mostly found in laptops, but soon, hopefully, a more powerful versions will be released. And while we haven't ourselves tested it, our users reported that we can actually run just fine on Apple M1 GPU as well. So yeah, that's quite a range of things we support. And we also run on Windows, macOS, and not only run, but actually are included in the official repositories in multiple Linux distros. To do all of that, we require quite a lot of code, namely almost 500,000 lines of it. And this project has been going for more than 30 years already. So while we try to keep things modern, up-to-date and clean, of course, we do have quite a bit of legacy. And of course, to run on big cluster machines, we support MPI for multi-node parallelism, but we also support OpenMP for parallelizing the workload within one node, and SIMD for effective use of each CPU core. And for supporting GPUs, we have CUDA, OpenCL, and since recently, SYCL, which is the focus of today's talk. Now, what exactly are we accelerating here? Yeah, so we are doing quite a lot of work. What is this work? Molecular dynamics is very similar to the very famous toy example of n-body problem that's very common for in most, I guess, of GPU programming courses. Except we have slightly more complicated physics, but yeah, it's iterative problems when we first compute a number of forces, reduce them, integrate, get the updated particle positions, etc., 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 and repeat it ad infinitum. And the problem is here that each single step to have consistent physics must be very small. In terms of simulated time, it's around 1 femtosecond, maybe 4 femtoseconds. Well, we need to simulate up to milliseconds if we want to capture any interesting biological phenomena. So we need to do billions of steps for if we want to do any interesting science. And another limitations that is enforced on us is the system size. While on large machines we do want to run big systems with millions of particles, very often actual real systems that people are interested in simulating are small, maybe tens or hundreds of thousands of particles. So we are very interested in strong scaling. We cannot just say that, oh, well, on this big machine, we'll just run a bigger system. Yeah, sure, that's a relevant use case, but we are also interested in being able to run small systems on those big machines. So we are interested in strong scaling and also in low latency, because we do need to do many iterations. We need to do each iteration as fast as possible, and we cannot just add more work. Very often we are actually limited by the scheduling, by how fast can we dispatch the work to the GPU. We're talking about GPU acceleration. And besides, we do want to support multiple types of simulations. Here we have one of the real computational schedules. We have multiple overlapping work on CPU and GPU, multiple kernels running in parallel. We have communications with other nodes. And in ideal case, we get a pretty good overlap. But sometimes, for example, we might prefer to offload all the work to GPU just to avoid unnecessary synchronizations. Sometimes we have some work that must be executed on CPU, so we might want to support a different distribution of work between CPUs and GPUs. Sometimes our system lacks some of the forces that are present here. For example, the PME mesh calculation is only relevant if we have PME. If not, this block is absent. So we also have to support a wide range of possible schedules and of possible ways that work can be offloaded or not. Now let's rewind 2 years back. GROMACS 2020 release, we only supported 2 GPU frameworks at the time, CUDA and OpenCL. CUDA was our primary, our focus of development work, because most of the big machines used for high performance computing used NVIDIA GPUs. The framework was most mature, had most features in it. And yes, that was really the most relevant target, and at the time, the best way to allocate our resources. And we also had OpenCL that we used as portability layer, so we could technically run on AMD and Intel GPUs, but it wasn't really focused effort on our side. We had some support for it, it was improving, it was optimized, but it was not actively developed, because at the time it wasn't really that relevant. And we also had separate, sometimes with manual SMD optimizations, versions of the same functions for CPU. But things are changing. If we look at the most recent top 500 list, the first and third place are taken by AMD machines, Frontier in Oak Ridge and Lumi in CSC in Finland, and Argonne laboratory hopefully soon will have Intel-based machine with up to 2 exaflops of performance. So obviously focusing only on CUDA is not really possible if you want to stay relevant in the coming exascale age. So, okay, why do SYCL? Why not continue, for example, using OpenCL or use some other framework? First, SYCL is an open standard, which is a big benefit for us. GROMACS is also an open project. GROMACS has 30 years of history and hopefully will stay around for quite a long time. So investing in some proprietary standard that can live or maybe can be abandoned is not great. Being open standard kind of promises that probably it will stick around. It's also implemented on top of existing backends. It doesn't try to reinvent the wheel, so it already leverages the existing device compilers, etc. So it can be used now. We're just fine, even if it's not directly supported by the device vendors. And unlike OpenCL, it is standard C++ code, just with custom library and probably custom compilers. But we don't need any additional support from all the infrastructure around our code, like code formatting, things highlighted in IDs, linting, etc. It's already included, and with some focus of SYCL eventually merging together with new C++ executors and other standard developments, probably it will, one way or the other, make it into the C++ standard, which also promises bright and long future. And besides, we already have OpenCL implementation, and SYCL is structured in many ways similar to OpenCL. So, unlike more exotic approaches, we don't really need to extensively modify our code. We don't need to really rethink the logic of how we do the GPU offload. So the whole project of SYCL porting started in September 2020, near 2 years ago. And initially it was focused on Intel GPUs and was run in the scope of Intel One API Center of Excellence here at KTH. By January 2021, we released first SYCL-enabled version. It wasn't part of the main GROMACS release, it was a special version with support for offloading the most compute-intensive kernels for Intel GPUs, but it still worked and was pretty high performant for the hardware it was targeting. 1 year into the project, we decided that we will also officially support SYCL for AMD GPUs. It will be the main official recommended means to run GROMACS on AMD. And the next GROMACS runs on yearly release schedule. So February 2022, GROMACS 2022 is released, and SYCL is now part of the main release. It's not any special version, and it supports most of the GPU offload features supported in other frameworks. In fact, actually now more features, more offload schedules supported than OpenCL. And it is shown and tested to work on hardware from all three vendors. Which decision we had to make on this journey? First, we have to decide whether we want to use any of the automatic conversion tools that promise to take your CUDA code and magically transform it into SYCL. And for many projects, it can be nice. Also, yeah, it takes your code, almost no effort, and it produces something that's more or less maintainable. Probably not the cleanest code, but still. But we don't want to just do blind conversions. We want to have both CUDA and SYCL. We don't want to replace CUDA with SYCL. So we want to keep the code very clean. We want to leverage already existing abstraction layer for different objects like device, queue, stream, etc. that we had for portability between CUDA and OpenCL. And besides, our CUDA kernels were already heavily optimized for NVIDIA, and porting those optimizations to AMD or Intel didn't really make any sense. And the most effort was actually in making this abstraction layer nice and clean. Rewriting kernels is a busy work, but usually not that time-consuming compared to actually architectural decisions. So we didn't use any of the automatic conversion tools. And we also, at the moment, didn't use the DAG-based scheduling. So in SYCL 1.2, it was the only officially supported means of scheduling when you have events from each submitted task, and you use them and the buffer accessor mechanism to automatically parallelize your application, which is good and nice in theory. You don't have any data races, you get your tasks automatically scheduled in parallel where possible. So it should be nice. It should help you as a programmer to make your code less buggy and more performant. Unfortunately, in GROMACS, we already did most of these works that runtime is supposed to do. We already run things in parallel, in multiple in-order queues where possible. We already do a lot of synchronizations. So we already invest all this effort, and actually runtime won't save us from that. It's already sunk cost. And besides, runtime must be really smart to outdo all these manual optimizations. And actually, in our cases, in our short, small tests, it seems that actually, at least currently, SYCL runtimes are not as good as what we did. We don't get as good level of task parallelism as we achieve with our manual scheduling. And besides, since we anyway want to support CUDA, which forces the use of in-order queues, doesn't have any convenient way of event-based test dependencies, we will have code divergence. You have implicit tag-based synchronization in SYCL and our manual in-order queues for CUDA. Not great. Our scheduling code, to be honest, is already a bit of a mess, and making it two messes won't help things. Probably with our experiments in CUDA graphs and some similar related developments in OneAPI and SYCL, we will be able to ditch in-order queues and actually focus on graph-based scheduling, which hopefully will make a lot of things easier. But since at the moment we still have to use in-order queues, we decided to just use them all the way everywhere, use manual memory management with USM, and keep things maybe not simple, but at least uniform for now. As I mentioned earlier, originally the project started with only Intel GPUs, directly targeted using the Intel OneAPI framework. And later we added SYCL in order to target AMD devices. Now there is an active work by Codeplay to add support for AMD devices in Intel OneAPI, but since the decision was made almost a year ago, only SYCL actually supported AMD GPUs at the moment. So how it works in practice? In theory, Intel OneAPI and SYCL implement the same SYCL standard, right? But in practice, of course, just like theoretically, the same code should compile just fine with GCC and Clang. If you have a big code, a complicated code base, it's not always works out of the box. But it was pretty easy. We had to work around some backend and compiler issues. Porting to SYCL actually helped us find some bugs in our code that worked with OneAPI but were not standard compliant, were not logically correct. Of course, for new GPUs, we had to redo some of the optimizations. Luckily, we already had a lot of them in our OpenCL kernels, And we had to still invest some work to find out places where compiler didn't quite optimize the code we intended to do. But yeah, getting the code just running required pretty minimal and localized fixes just to work around some missing bits, because neither OneAPI nor SYCL currently fully implement the SYCL 2020 standard. And unfortunately, we had to do quite a lot of CMake scripting, which is not probably real programming, but if we do want to support users running on different hardware, different machines, we want our code to be able to configure and compile there. And at the moment, that required quite a lot of this pretty, in my experience, unpleasant but necessary work. But yeah, overall, it was much easier than, again, separate implementation, like 98, I guess, % of the code is totally identical between SYCL and OneAPI branches. There are only a few bits that we had to use preprocessor to work around. And one of these bits is FFT. Because in GROMACS we use three-dimensional FFT, and currently there are no SYCL native libraries. We have one MKL, but in it FFT is support only for Intel GPUs. It's not part of the open source OneMKL implementation. We obviously have QFFT for NVIDIA and ROCFFT for AMD, but they require using the interoperability to mix the native GPU libraries and SYCL libraries. And it also was one of the reasons we had to do a lot of CMake scripting, because we had to find the correct library locations when we are using, say, SYCL or Intel. So unfortunately, currently there are no really portable and SYCL native FFT libraries. So if you want to use FFT on multiple backends on multiple hardware, you will have to do all this wrapper code writing yourself. Now there are libraries that promise the portability. There is VKFFT that supports level 0, CUDA, HIP, and OpenCL, and Vulkan. So it can be one library to rule them all, so to say. And we are actively exploring, because it's also showing pretty good performance on all the hardware we're interested in, but still doesn't have SYCL native wrappers, SYCL native bindings. So we'll still have to do this dance with backend interoperability. And for multi-node parallelism, there is FFT that also can parallelize the FFT over multiple nodes or multiple devices, and can internally use several backends. But yeah, that's something we are looking at, but not currently using this SYCL. And well, after all this work, what did we get? These are not the most recent results. I guess they're from late spring. I haven't been able to rerun all the tests since then. If we look to the right at kernel performance, we're comparing here our SYCL port to the experimental native HIP port done by AMD. So that's hopefully pretty respectable baseline we are dealing here with. And it turns out that some of the kernels here are much faster than even native HIP kernels. Those kernels at the bottom are usually pretty fast and don't take a huge chunk of compute time. Here on top are more important kernels, and sometimes they're 5 to 10% slower, but still, I would say that is a huge success for SYCL that we are getting performance near native. We haven't really explored in depth what are the reasons for those small performance gaps or for those performance gains, but yeah, probably some minor compiler things. And yeah, total kernel time here in dashed line, again with SYCL turns out to be smaller than with native heap. But unfortunately, if we look at the whole application performance on a single GPU, we see that for small systems, here we see the number of atoms in a simulated biomolecular system, we have a very big overhead. The SYCL port is up to 60% slower. And in our investigation, we found out that it's related to the host submission latency. So molecular dynamics is an iterative problem. We want to do many iterations per second. We want to submit a lot of work. And if we don't have big kernels, if we have few atoms and the kernels execute very fast, our performance is determined not even by GPU performance, but by how fast we can supply work to GPU. And here, since SYCL runtime is supposed to do much more things than just native heap, we are getting this overhead. Hopefully now, with more recent SYCL versions, performance should be better because we interact with Axel, the leading SYCL developer, and he, based on our feedback, he incorporates some of the fixes to reduce the submission latency. But that's not something we had time to evaluate just yet. The patches were submitted like a week ago or so. And besides, here we are also seeing the problem with runtime being not smart enough, because with heap, when we submit two kernels into parallel in-order queues, we get them executed in parallel with perfect overlap. But unfortunately, since even in-order queues in SYCL are required to respect the events, we can use in-order queues theoretically with, say, buffers. So runtime still has to check a lot of events, and sometimes it doesn't do the best possible job, and sometimes the kernels that can run in parallel are actually scheduled sequentially, which also contributes a bit to this performance gap, while yeah, each kernel itself runs faster. Now for Intel, it was run on DG1, which is discrete Intel GPU, but still probably low-end ones if we are talking about the HPC scale. And here we see that compared to our OpenCL port, actually kernel performance is a bit worse in some cases, again a bit faster, but still relatively the same. We tried running with two different backends, the SYCL over OpenCL or SYCL over new Intel level 0 backend. As expected, it didn't have any noticeable impact on individual kernels. It's mostly the way those kernels are scheduled. The kernel code is the same in both cases. But we do see some differences in the application performance. Level 0 here shows that while kernels actually are slower than native OpenCL, SYCL running over level 0 is somewhat faster, because level 0 offers lower submission latency than OpenCL. Again, for small systems, we get this benefit because here the situation is reversed. SYCL runtime is doing a better job than its reference. But yeah, for bigger systems, we have this region where the runtime is more dependent on individual kernels and not on how fast it can schedule them. Now for NVIDIA, we actually haven't put a lot of effort into optimizing our SYCL port for NVIDIA performance. And as you can see here, some kernels at the moment are almost 20% slower, 20 times slower. Likely that some missing compiler optimizations or other more or less localized thing. But yeah, while we haven't decided to actively target NVIDIA devices with SYCL, we also obviously wanted to test how this performance portability things works out. And yeah, in general, it's not too bad. Of course, yeah, some kernels are probably 50 times slower with SYCL or Intel One API compared to our native CUDA port. But also that's pretty tough baseline. A lot of effort has been put into making our CUDA code as fast as possible. It was the main development focus for many years, so it was tough to match. And yeah, besides, we haven't really had any dedicated effort into optimizing our SYCL for NVIDIA GPUs, because for that we have CUDA. We just are very interested in having some portability. But yeah, even without any dedicated effort, simple, fast kernels usually perform equally well with SYCL, Intel, VM, and native CUDA. More complex kernels here are slightly slower, but probably it can be fixed if enough effort is put into that. And again, we are seeing that for small systems, the whole application performance suffers due to large host side overhead, and it more or less evens out and is mostly determined by kernel performance later on. So if your application is latency sensitive, you should probably look to the left side of this graph. If you have bigger chunks, bigger tasks that you're submitting GPUs, tens and hundreds of milliseconds, probably the right side of the graph would be more relevant for your case. And yeah, what other nodes can I mention from this journey is that performance portability is actually great. It's not only about code reduction, it's actually about ensuring, not about avoiding duplication, but also ensuring that your code works correctly. We can use NVIDIA Compute Sanitizer if we run our kernels with SYCL over either SYCL or Intel One API. And yeah, it actually helped us find one bug in our code. So yeah, even if we don't intend to use SYCL on NVIDIA GPUs actively, being able to do so is still very nice. We had some success with our currently experimental, not yet released work in using GPU-aware MPI to avoid having to stage the data from GPU to CPU and send it between CPUs and then back to GPU. To use DMA to directly send the data between different GPUs. And yeah, since SYCL is based on the existing backends, it's built on top of CUDA and built on top of ROCm, we can use those, the GPU-aware MPI that is built for those backends. And it works quite well, no SYCL-specific issue there. But yeah, it's not natively integrated, so you will have to use USM to get actually raw pointers to device memory to pass to the MPI routines. But yeah, it works just fine. You can totally use it in your production applications. And another sort of warning, probably in a way for future SYCL users is that, yeah, SYCL, the whole ecosystem, is not as mature as CUDA and OpenCL. Yeah, it's good. It's developing really fast. We get new, interesting things added. We have much more experimentation. We have much more exciting things happening. But also that means that you probably need to put a bit more effort into maintaining your code. Because, yeah, even if your code works with one version of the compiler, probably some of the features you used would be deprecated later and probably even removed. Sometimes, yeah, a bit more bugs are introduced than you would expect with new CUDA releases, say, and also such things as, for example, error reporting. We're talking about both runtime errors and compile errors. It's not great. Sometimes it takes quite a lot of effort to figure out exactly what's happening. But yeah, it's hopefully being remediated, and it's already getting better, and as SYCL grows more mature, it will go away. But yeah, if you're interested in adopting SYCL now, be warned that probably you'll have spent a bit more effort to just maintain your code than you would have with, say, CUDA or OpenCL. So yeah, to conclude, SYCL actually achieves its promise of performance portability. You can write your code for Intel GPUs and Monday Pay, and only trivial changes will be required to get it running on AMD devices or Intel or NVIDIA devices with SYCL. So yeah, it's performance, portability, it's there, but probably if you really want good performance, you'll still have to add device-specific code. The compiler won't magically optimize your code for totally different architectures. If you write code expecting, say, specific subgroup size, obviously you will have to specialize it for different hardware. And even then, sometimes there might be compiler bugs or runtime issues that make it a bit harder to get good performance. But yeah, it's possible, but not trivial. If you have experience writing code for CUDA or for OpenCL, it shouldn't be world-shattering to switch to SYCL, but a bit easier with OpenCL. In CUDA, some ways, say, synchronization is handled is pretty different. So if you have CUDA and OpenCL in the same code, it might require some re-engineering if you rely on, say, barrier synchronization. Besides, currently, yeah, SYCL is new and not a lot of libraries are there. You have tons of FFTs, BLAS, RNGs for CUDA, but for SYCL, not so much native libraries. But you can use interoperability and device native libraries, the same QFFT, for example, from SYCL just fine. And yeah, things are changing. Hopefully, things will get better. We'll get native libraries. We'll have more optimized runtimes. We'll have smarter compilers. So a lot of those issues will go away. In the end, I would like to thank Intel for funding my work in the scope of KTH One API Center of Excellence. Specifically Heinrich Bockhurst and Roland Schulz from Intel for their help. Axel Alpay from Heidelberg, who is lead developer of SYCL. AMD and StreamHPC, who shared their heap port, which was used as a baseline here, and yeah, as an inspiration for some of the AMD specific optimizations. And of course, the rest of the GROMACS development team. If you want to learn more, you can go to our website or our GitLab. Submit bugs if you encounter some more suggestions. Here is the paper describing our parallelization scheme a bit in more details, although nothing specific there. And if you have questions, feel free to reach out to me via email. Thank you.
Yeah, thanks, Andrey. That was very enlightening and interesting talk to find out a bit more about your experiences, and I like the fact that you went into some of the kind of details of things that you liked and didn't like as well, because it's good to hear about both sides of things. So thanks a lot for joining us to do that. I really appreciate it. One thing I was going to ask about, perhaps start a bit of a high level, is kind of like, what's your personal focus? Are you C++ developer or molecular dynamics expert, or kind of where does your background come from?
I would say a bit of both. So I have PhD in computational modeling, so it's, I would say 50-50. Currently, I'm mostly working on the development and not on the modeling things, but in terms of background, it's a mix.
Yeah, that's good. That's interesting. That must make your job quite interesting, getting to take on some of those different challenges as well. And one of the other things you mentioned was about how GROMACS has been used, I guess, particularly involved in analyzing things for this kind of more recent COVID virus and things like that. So does the project work quite closely with different researchers around the world?
Yes, we actually have a whole team on our very floor who are actually using the GROMACS for membrane protein modeling as well as experiments. So we have a wet lab doing actual in vitro experiments here. People who do the experiments sometimes use simulations, sometimes you have, some people do mostly simulations, but yeah. While most of the core developers are doing, well, the development and not very much involved into biological experiments, but yeah, we do have people who do the experiments both numerical and wet, so to say, right, sitting on the next table.
That's really good.
I guess that is necessary if you actually want to develop any value. You need to see your users interact with it. I don't think we'll be able to actually get our code that popular, get such wide adoption if we were just developing in a vacuum.
Yeah, absolutely. And one of the other things I was interested about, because it's an open source project, do you get lots of contributions from different individuals and groups? Because I guess there's a core team that you work in, but there's other contributors beyond that.
Yes. We do have occasional one-off contributor. Usually it's based on more or less established collaborations. So it's very rarely we do have like random people just doing small fixes. Also, it happens, but yeah, it's a bit niche code. Of course, yeah, I was bored in how popular it is, but probably still it's not as widely used as many more open source projects, like, I don't know, like Python. Yeah, it has much more users. Compared to it, SYCL is, GROMACS is pretty niche.
Yeah, sure.
Yeah, and usually it's still based on some academic collaboration. But yeah, we have people contributing code, some people maintain their own forks. If there is something that we are not ready to accept into the main line.
Cool. That makes sense. That's good. Good to know. And one of the other things I was going to ask about was the project already used OpenCL and CUDA, as you talked about. Did you end up using any interoperability between SYCL and CUDA, or did you end up just kind of rewriting kernels?
The kernels were written. Yes. We did have to use some preprocessor magic to call the native CUDA heap functions in a few places when there was no direct SYCL version, and using the native function provided enough performance benefit to justify that. But in the end, yeah, writing kernels takes some time, but usually not that big. And for example, yeah, it's possible to use things like Alpaca or Cocos to have the same kernel on for multiple backends, it's possible to just come with some preprocessor-based solution to compile the same code for, say, in CUDA and OpenCL, because kernel logic is more or less the same. But for now, we are just duplicating the code. Probably not ideal in many ways, but that's something we have to accept for now.
Yeah, sure. Sometimes you need to make decisions about technical decisions that go different ways. So that makes sense. Cool.
I wondered if
sorry,
I could ask, what's next? So you've got these promising results with SYCL on Intel, AMD, and NVIDIA GPUs. You were pointing out there might be some work to do to close some of the performance gaps, both in the kernels and the runtime. So what next? Are you planning on addressing those, or?
Well, we really hope that somebody else will address the runtime gaps.
Mm-hmm.
We are interacting more or less closely with SYCL, with Intel, and some of SYCL Play about the possible runtime problems. But now the main focus for GROMACS is on porting the rest of the features and specifically on multi-node parallelism. As I mentioned that we did some experience with GPU-aware MPI, that's where currently most of the work is happening. We want to be able to not only run on a single machine, that I showed you were for a single GPU on a single machine, we want to be able to parallelize on those big top 500 level machines. For that, we need to port the rest of the CUDA specific code. It is, in our case, CUDA specific. Such feature is not supported with OpenCL in GROMACS. So that's where work is happening now. And also, unfortunately, quite a lot of effort is spent on just testing on different configurations because currently SYCL implementations don't always work on any random hardware because, usually for, say, Ubuntu, you can just download and run installer. If it's some Cray machine, and we do want to support them, it might be more complicated. So that is a bit of a time sink now.
Thank you for the talk. It was great. Great to hear.
Yeah, that was really good. Really appreciate it. Thanks for your time, and I know how much effort goes into preparing for these things, so I really appreciate it.